So if I repeat the content of assignment number 3, and in assignment number 3, there was all these different questions. I asked you to create different models, and the last question was like I asked you to come up with your own compound. So this was like a mini project for you. Like if you remember from starting number assignment 1, like when you initially learned how to uh, represent the structure on the computer, then how to estimate the descriptors and how to again estimate the activity, because using which you can come up with the best possible compound. So this seventh question I could have asked in a different way, but that time you didn't have knowledge about what topic I'm going to cover today. So that's why I asked you something like that. You just have to, I said, replace the R group and just find out whether the compound which you have found, it is having good antibacterial property or not. So what could be this the group R which you have chosen? Did you choose it randomly, or did you use some criteria before you concluded whether the compound that you are considering is good or not? Like I said, if the values you are getting 17.34 or something between this and 22.78 or more than that, so if you are getting more than 22.78, so then we said it is one of the best possible drug. So what could have been the good criteria for you, based on, even though you didn't know the method what I'm talking today, but what criteria? Suppose if I would have forced you guys to tell me the compound which should be having the activity value of 22.78 or more, what would you have done? Can anyone answer? If I would have asked you, like, I don't want any compound, I don't want any compound activity 17.34 or anything less than it, I want something more than 22.78, of course. So what you guys would have tried?
So like we have already a molecule that has this activity, so we can try to alter the same molecule some atoms, or we can look into the molecules that have same property as the existing molecule that we have, with property of
Yes.
22.4.
So you had 6 compounds. Out of that, which compound you would have focused on?
The one that had the highest activity from our models.
The one which is having the highest activity value, because you are looking for the same thing. You are looking for the higher activity. So if I have 6 compounds and I would asking you to find the best possible compound, I would find something which is already having, out of the 6 compounds, like you can consider, lowest had the 17.34, highest is having 22.78. So that functional group I would have little bit tried to tweak. What could be the concept for me, that that is what related to the today's topic, that if some compound is similar, so there is a some optimism or guarantee, you can say, that that could be also the one of that particular compound will be also having some similar properties. So if some compound you are trying to tune, which is having some 22.78, it might be possible that if you are changing the structure a little bit for that, by again thinking about this criteria only, you might get a compound which might be having similar or even better properties than that, instead of choosing the compound which is having just 17.34 value. I hope you are getting what I'm trying to say. Like using this, if you know this method where you are actually focusing on some kind of similarity between the compounds, so you would be choosing some compound which would be similar to the activity of this compound rather than choosing this. Now you will say like, okay, for all the compounds, till this part everything was similar, right? Only this part. But here also you could again go at the level of similarity, that only the components which is having 22.7, you will be focusing on that rather than which is having the 17.34, and accordingly you can try to tweak. So there is a more chance you'll do. So that is what the method I'm saying I will talk today, and this method is again a method which is related to a ligand-based method, where you can consider we do not have some kind of idea about the receptor, and using that we can use some kind of similarity search. And using the similarity search, we can identify one of the best possible compound with our criteria. Okay. So if you read some of this theory, you can consider they say the chemical similarity is one of the most important concepts in chemical informatics. Again, you are using for drug design studies or material design studies. You are interested if you already know that some compound is good, but it is having deficiency. So you can actually try to find out the other compound, and accordingly maybe you will be fine. Like for example, like do you know, like generally for pain relieving or fever we take paracetamol. Similarly for runny nose or allergy, what kind of component do you normally have for allergic conditions or something? We take some antihistamines. If anybody knows the name of the cetirizine, right? Cetirizine you might have heard about. So cetirizine, if you take many times you have cold, that time also you take. So what are the side effects? One of the most common side effects. Dizziness, right? So dizziness, sleepy. So what people will do, they know that cetirizine is the compound which is good against this runny nose, allergic, but it has a side effect of dizziness. Now they want to have one property but not the other one. So that's why like with time people have again did this kind of studies, maybe the experimental one also, and they have come to know that okay, cetirizine itself it has the mixture of leo and dextro form. So if you take the leo cetirizine, this time most of the doctor when they will prescribe, they will prescribe instead of cetirizine, they will prescribe leo cetirizine. So you can come to know maybe it is having, like I have tried to read on the internet, some cases, some studies do not agree with that a lot, but at so many places it has written that the sleep induction or dizziness, the effect of levocetirizine, it is very less. So that's why doctor mainly prescribe that. So you can consider this is how, if you see, if you already know that cetirizine is a good compound, so by the concept of chemical similarity, you can find out some other component which might be useful to you, and you can also, it could be useful for removing some side effects also. So this is the concept, because based on the answer that you have given me for the assignment number 3, like you compound which is having some activity of 22.78, and for that you will try to identify the similar compound. Why will you try to choose that compound? Because you internally know that structurally similar molecule, like they will be having some similar properties, and this is actually very well known. Like even this is not just your assumption, but it is known that some molecule, if you take similar molecule to that, they will be also having good amount of biological activity. So this concept is called as something called as neighborhood behavior. Okay. So what you can do always, if you already know some compound which is good against that, so you can use this similarity search method, and you can hope that you will get some other compounds which can be good for your own purpose. Like to give an example, this is another good example. If you know there are so many addictive drug molecules, so which act against this opioid receptor, and this cause the like these receptors are responsible for your even the sensation of pain also, and also addiction and other things. So if one component which you know, this is one of the infamous drug molecule which you know, so if you see their structure how it is active against this opioid receptor, similarly the other components also where you can see some minor changes, they will be also active. Like this is known experimentally that all these compounds which are looking similar, they are active against all these opioid receptor. So the question comes to us now. We know actually that certain compounds are good, and now we want to use in this particular method that which are the other components which are similar to this. So when I'm saying about similarity, what will be your criteria? How will you basically decide whether the two components are similar or not? What will be your criteria to decide whether the two components which are given to you are similar or not? And that you have to evaluate computationally. Yes, any answer? How will you decide whether the two components are similar or not? Okay, I guess at least you have something in your mind. You have not. Okay, let's answer this question. Which two are the most similar? Okay, banana, orange, and basketball. So which two are the most similar?
Orange and basketball.
Okay, orange and basketball. Any other answer?
Banana and orange.
Banana and orange. Any other answer? Okay, so if now we can go back again to the previous question. How will you decide whether two given structures are similar or not? Again, it will come to the level of criteria. What criteria you want to put? Accordingly, the computer will tell you. So here, if you have the criteria of some kind of like spherical geometry, if you are looking, so then orange and basketball will be similar. Then there is no question of banana. If there is the question related to fruit, so then banana and orange will come. The same way you can consider like what criteria you are choosing, accordingly the two components will be considered to be similar. Even there could be one of the criteria like the banana is starting from B and basketball is starting from B. So then there you can consider some kind of similarity. So it is again like depending on what criteria you are choosing. So that's what you have to tell to the computer so that it will identify similar compound. So there are so many things, different things for identifying these kind of similarities, and day by day the methods are evolving. So some of the methods you already know, like there are methods called structure search. Then there is another term called as substructure search. Then 3D pharmacophore search, and finally, what is important to us is the similarity search. Okay, these things are different from the earlier one. So what are the difference? Now, if you talk about the structure search, this is simply you have already done. When I had given you the assignment number 1, and maybe you were trying to, or assignment number 2, assignment number 2, where you try to identify the molecular descriptor values, and you were trying to confirm by looking into like for some of the components molecular weight is not matching or something. So for that you are trying to go to the internet and try to see whether what molecular weight I have got, whether it is matching this. So you had done some of the databases you already know. So there you try to just put the molecule name, and inside some processing will happen and it will give you all the details of that. So this is like the simplest thing. Just you have all the huge database, and if you are interested to look for like some boiling point of a particular component or the price of a particular component, you can simply do a search. So this is a very good website called as PubChem. You might have seen it earlier. This is the new interface of that. You can search for any component by name or by the structural details or even by the smile string, or even if sometimes you know the compound number. So simply by entering that 3-digit or 5-digit number, you can come up to know all the details. So this substructure search is something, I said this is the new interface. What I'm going to show, like every time the interfaces change, this is something like maybe 2 years back. So you can consider in the earlier version, you could have simply done the structure search. You could type something and get the details. Like for example, if I type benzene, so I will get all the details of this. Or if I know the number for that, some particular number, PID number will be there. So that also can give me the all the details of that, all the chemical and physical properties. So if I enter some number like 241, so something inside there will be programming done that how the 241 number is exactly going to be benzene. So for when you have a huge database, so you don't want to waste time with analyzing all the characters. So by simple numerical digits, the searches are made actually very easier. So all the different details you can get by simply this structure search. Now, what is exactly substructure search? So by the name you could understand that there will be a whole structure, and the part of it, it will be called as substructure. Okay. So for example, they say like substructure searching is the most common method when people try to identify the compounds of interest, and a substructure search identifies all the molecules in the database, each and every one that will be containing a specified substructure. Like for example, your substructure, if it is a consider a aromatic ring, or if it is a carboxylic acid group, or alkyl chain, C5 alkyl chain. So if you hit that query, all the structures that you will be getting from the database that will be having that particular substructure. So for example, if you are interested in some query like this is a dopamine derivative. So you can see here, you can find out some component like adrenaline or even this olmedin, which are actually matching to this particular query a lot, like close to 90% or more than that. But along with that, what is going to happen? You are going to get again so many different component, maybe even the bigger component, which by your substructure search you feel that okay, that particular part you have found out, but this might not be very close to the compound. Maybe if you find out the similarity in just by looking at the two, you might see like the structure is just 50% similar, or even maybe up to the level of 5 or 10% it might be. So this is sometimes useful, but in many cases you don't know exactly whether to your particular thing, suppose for your assignment what a component you had, and if you simply use the substructure search, so all the components what you are getting, they might not be useful to you because there is no such criteria you have given other than your part of the molecule. Okay, so that's what slowly we'll try to evolve. So suppose if you want to do this kind of substructure search on the PubChem website, so you can consider there is this tab of substructure and superstructure. Now here, what you can do, you can simply enter the smile string of whatever compound you want, or if you have any PDB file, so you can upload the PDB file, or you can even the facility is there to draw the structure. Okay. So then you have to select from this option whether you want a substructure or you want a superstructure. So what is this substructure and superstructure? Substructure you would have understood that it is part of the bigger molecule. Similarly, the superstructure will mean that for this particular component, the entire part should be there, and along with that, something else should be also there. So you can consider in the substructure, like ethanol is the substructure of acetic acid. Okay, ethanol is the part of this. So ethanol is the substructure of acetic acid, and acetic acid is the superstructure of ethanol. Okay, it is the bigger structure. Superstructure, it is a bigger structure. Now, when you are going to do this kind of searches and you want to identify the substructure, they say when you do substructure search, you do not actually get substructure, but what do you get? You get superstructures. Like whenever you hit for this query, like you are entering some smile string, you are getting superstructure, even though you are asking for substructure, but this means you are just providing a substructure, but this is going to give you all the bigger structure. So if what here, if you see this particular example, this I had taken from your assignment only the R group I had changed with the H, only R I have changed with the H, and I try to identify the all the different compounds. So if you see here, they say, yeah, this component, particular component where I change this R group with the H, it is called as sulfanilamide. So when you do this kind of substructure search, always you will be getting so many compounds where the this particular uh, thing will be matching. So it will give you each and every compound. So you can consider there are 29,344 compounds where this particular substructure is available. So this compound number one, always it will be matching with what query you had. So this is particularly matching with the sulfanilamide. So this is given at number one. Again, but this is not ordered in a particular way. There is no some criteria where this has just given you all the components randomly. Even by surprise, at fourth number, it has given you a compound called as sulfur diazine, which was one of the component from your assignment. Compound number one. So this also it say that it is matching with this particular substructure. So when suppose if you are taking again this as the query, and if you are looking for the superstructure, so what do you think? What will you get? Suppose if I enter the smile string of the sulfanilamide, If I hit the query for the superstructure, what am I going to get? You can consider here like all the different component of the entire structure. This will be shown here. Now here again the first thing, it is going to 100% match. This should be considered again the superstructure of the original thing. So that is again coming, but slowly step by step you can see there are the parts of these components, or you can see the fragments of the components. These are nothing but actually they are the substructures, but they are being shown in the superstructure search. I hope you are getting this what I'm saying. It is mentioned clearly. It should be noted that the substructure search does not give you substructures of the query, and the superstructure search does not return superstructure, but it is the opposite way. So here some question might come, like you can clearly observe like this kind of structure water is showing here. This is exactly matching. This is also being matching. But what about this? This is simply, it is saying that water molecule is present in this structure. So what exactly happened? How the water is coming as the superstructure of the sulfanylamide? Or again the same thing, yeah, just consider water. So here if you observe there are some oxygens, okay, but there are no hydrogens attached to it. But here again the criteria, every time water you are searching, there will be some filters. So in the filters there will be again option, like you had in the open babel option, like I want the hydrogens to be included, hydrogens not to be included. So when the hydrogens are actually they are saying that it should be suppressed. So only even if it is finding out the single oxygen, it will automatically satisfy the valency, and it will say okay, in this particular entire structure this particular substructure is also present. So that's why it is saying that water is also present. So that was about the second thing, substructure search. Now there is a more sophisticated search method. It is called as 3D pharmacophore search. Now, in the earlier method of substructure search, you are just looking at the particular part of the molecule, whether it is matching or not, and because of it, it was just generating all the different compounds. So you can make these kind of searches even more sophisticated. Like still, I haven't got to the level of similarity search where it will be actually ranked properly. Here we are seeing some kind of only randomized searches. Only some components will come based on what query you are being making. So if you see what is this exactly pharmacophore, the meaning of this word is. So in the earlier substructure search, you are focusing on geometry, right? So here in the 3D pharmacophore, along with the geometry, like they are saying, their spatial relative orientation will be considered. So geometry will be considered, but apart from that, a set of features will be also considered. So when both the things are matching, so then only that compound will be considered to be similar. So this is like you are going one step ahead. You are not just looking at the structure, but you are also looking at some good features. So what kind of features you could look for? You could look for, these are the regular things which we have earlier studied also, the hydrogen bond donors, how many hydrogen bond donors are there, how many hydrogen bond acceptors are there, how many positively and negatively charged groups are there, how many hydrophobic groups are there, or aromatic rings are there. Based on that, both the things like the geometry as well as the features, it will come up with whether the particular structure is going to match with the other compound or not. Like for example, this is your particular query for the 3D pharmacophore search. So you can see here, this is a more sophisticated query than the other one. Here they are mentioning some criteria, like there are two benzene groups, and then again some kind of ammonia group is there, and they have given some criteria to identify the similar components, and this criteria is little bit flexible. This they are saying the distance between the center of these two things, it should be between 4.7 to 5.1 angstrom. Similarly between this and this also, if their spatial relative orientation, this is what was said in terms of defining the 3D pharmacophore, that their spatial relative orientation, it should be matched with the compounds in the database. And if other components also, the hydrogen bond donors, acceptors, all these components are also matching, then only the compound will be considered to be similar. So this could be considered as a more sophisticated method than your earlier simple substructure search method. Now, all these methods like the substructure search and 3D pharmacophore search, you are getting the compound. You are getting the compound which are similar, but there are limitations. What are the limitations? You cannot actually rank. Suppose I ask you like, okay, I want the only the particular compound which is having very close property. So that you are not getting. So for that you need to have some you need to reduce down this limitation. So first we should understand actually what kind of limitations are coming when we are trying to see the limitations of this our substructure or 3D pharmacophore method. They say always suppose if this is the ligand based method, and if you know that only there are some one or two active compound like weakly active compound, so how are you going to generate the substructure for this? Means this could be correct also, and in many cases it could not be correct. Like whatever substructure you are trying to come up with, using which you are going to make this query, so this might not be very accurate. Second, they are saying a particular molecule either matches the query or it does not. Means to your particular compound something will be matching, so those compounds will come, and something will not match. So this is what it is doing. It is creating a database, but it is dividing it into two different sets. Okay, there is no sense of any relative ranking. I hope you are getting what I'm trying to say. There is no, like, you cannot make any ranking out of this. There will be just matching or not matching. Then there is third limitation also, that you do not have any control over the size of the output. Suppose you want to have generate only a less number of compounds, like suppose if you are interested only in top 10 compounds. But with these particular methods, what is happening? All these 29,000 some molecules are coming into picture. So like if your query is very general, like for example, a simple molecule like benzene you have put, so this is going to generate enormous number of hits. Whereas if your query is very specific, so it will just give you a very small number of hits. So to reduce down all these limitations, we have this concept of similarity search. Okay. So in similarity search, what is going to happen? Even if you know a single active compound, you are going to trust that compound and you are going to make the search with that. So they are saying with this particular single active compounds also, you can proceed with your method. Second, each and every component which is going to have in your database, what is going to happen? It will be given a numerical score. Based on this numerical score, then you can do some kind of ranking. Okay, you are going to have a single active compound. This you are going to put into search. For all these compounds in the database, some score will be assigned, and all these scores accordingly in the ascending order or descending order, you can actually rank all these components. And again, the third use of this particular similarity search method is it is an iterative method. Like in iterative method, what do you do? In the first iteration, you reach to some best answer, and again that best answer is refined again and again. Okay, so it could be considered as the iterative method, where in the first step you have come up with some component, like these were your earlier compound. Now based on this compound you have made some query, and these particular compounds you have found to be the best one. And again, using these top compounds, again you can do the second iteration. Again whatever top compounds you are getting, again you can do this multiple times so that to your refine your criteria again and again. So using this thing, I could do the similarity search, and in the options, again, you can go into details of these filters and other things, but in the options, I will just focus on the score part. So here I have said like I want all the similar compounds based on some criteria, and the criteria should be greater than or equal to 95%. So whatever compounds will be matching at the level of 95% or more, so those compounds will be only considered. It will show and it will actually rank all of them. So if I do this, you can see here that again the sulfanilamide, the something is matching with itself to the 100%. So that is coming at number 1. But then at number 2, again you can find out some compound which is closer to this. Now here in the filters you could actually mention whether you want to have only the uh, single molecule or multiple molecule structure also. All this criteria here actually I think you can see the same compound again, but along with that there is some HCl molecule also. So that's why it is saying it is matching to this entire thing, but you could have the criteria that we do not want the structure where multiple molecules are there. So these kind of things could be removed from the searches. So maybe this will come at the second number, that this particular structure is matching to this particular compound number 1 with the some good score. Okay. So again the question should come to your mind, like what is again the meaning of this score? Okay, like I said, this compound is matching, this is matching with itself, so 100% score it is matching. Maybe this is coming at something like 99.9% match is coming. So what is this score based on which the ranking has been made? So again, I said the ranking which you want to do, as I had given you the example of this banana, basketball, and orange, and what criteria you want to choose. So this some degree of similarity you have to talk about, and this is actually subjective. There are no hard and fast rules. So when you want to talk about the similarity, so you want to evaluate two things. Okay, the first thing it is again you are going to evaluate some descriptors. Like earlier I had talked about descriptor which describes the molecules in terms of some number. In this particular cases, we are going to use only some specific descriptors. Okay, once you know the descriptor, then you are going to come up with some this degree of similarity, which is called as some similarity coefficient, which is going to based on these descriptors, this is going to calculate the similarity coefficient, and you can actually rank the compound. So what kind of descriptors you are going to use? They say like all these kind of search methods, these are like very old, even from mid 1980s, people know that. And people normally use the descriptor which is called as 2D fingerprints. And this is related to your descriptor, and they calculate the similarity coefficient, which is there are so many different similarity coefficient. One of the most famous one is Tanimoto similarity coefficient. So first one is the descriptor, second one is the similarity coefficient. So just we'll try to understand what are these fingerprints and similarity coefficient. So fingerprints, let's go to next. Okay, so fingerprints, what are these? These are nothing but some binary vectors where there will be some, you will count whether the presence or absence of a particular substructural fragment. Okay, earlier in the substructure superstructure method, I said if you have already a big compound and if you do a superstructure search, so all the different fragments of that component you can see. Okay, so now you can actually make use of those fragments. If the fragment is present in the particular structure, you will say okay, it is present. If there are two structure to compare, if it is some criteria you are having whether it is present in the one thing, so you will say okay, it is present, and this is the query. So here it, of course it should be present, but here also if it is present you will say 1, if it is not present means it is 0. So you can consider this is something like we are trying to actually see some kind of structural aspect, and we are trying to compare them at some minute level. So this similarity you can actually once you evaluate all this, 2D fingerprints, then you can evaluate this Tanimoto coefficient, which will be the measure of number of fragments common in between the two molecules. Tanimoto coefficient will talk about the degree of similarity. So let's see what is this Tanimoto similarity index, and then accordingly we can understand what is the fingerprints also. So suppose this is some formula I have. S is for Tanimoto coefficient, and A and B means how much is the similarity between compound A and compound B. So it is given by the formula small c divided by A plus B minus C. So what is this A here? A is the bit set to 1 in molecule A. Okay, I will explain in detail. Just know A bit set to 1 in molecule A. B is B bit set to 1 in molecule B, and C is 1 bits both common in A and B. Now, what is the meaning of this? Suppose there are two compounds to compare. So, if some fragments, now I said earlier it has been mentioned very clearly, these are the similarity is subjective. There are no hard and fast rules. So now this when you are talking about the similarity, you have to consider different fragments. So suppose if I consider 12 different fragments, like one of my fragments is the benzene ring. I will see in compound number 1 and 2 whether the benzene ring is present or not. So if benzene ring is present here and if ring is not present here, so A bit set to 1 in molecule A. So if there is one component I have found out in compound A, so I will say the total count of A has become 1. Suppose there is a hydroxyl group OH, and if it is present in compound number 1, I will write here 1 again. Maybe in compound number 2 also it is present, so I will write 1 again. So I am getting my count of A has become now 2, because bit set to 1 is here 2, whereas my B will be equal to 1, because only one thing is there, that is actually matching. Sorry, the one bit is there where actually this is present in molecule B. And C is the one where both the things are actually present. So C is something like this is for the hydroxyl group. So now my count of C will be equal to 1, because hydroxyl group is common in both A and B. So for example, if I am having 12 fragments and if I am having SAB is equal to both, now if there are 12 fragments and all the 12 fragments are matching with, if they are present in both the compounds. So what will be the value of SAB? If there are 12 fragments and they are present in both the components, what will be the value of SAB? So C, I said, where both of them are matching. So as they are matching, this will be 12. A, as in both the fragments are present in both, all the fragments are present in all the molecules. So in A also there are 12, in B also there are 12, and minus C. C was your 12. So how much it is becoming? 1. Are you getting this, what I said? My SAB has kept to 1. What does it mean? Okay, for those whom it is confusing, the next I have the actual table, so it will be very easy to understand. But you can consider that SAB value here, all the fragments are matching between the two compounds, so it is giving me a value of 1. Okay, so they say a value of 1, it is indicating that molecules have identical fingerprint representation. It could mean that both the molecules are identical only, or they might not be identical entirely, but what are 12 fragments? So all the 12 fragments are matching for them. So as per your criteria of 12 fragments, you will say it is 100% matching. So this kind of, you say like C is representing the similarity between both of them, and this bottom one is something again like a normalization factor. You had a normalization factor in terms of your R square value, right? So you get the values between 1 and 0. So similarly here also, to get the values, if it is the two structures are matching entirely with each other, so Tanimoto coefficient will be 1. If both the structures are not matching with each other at all, like all the 12 fragments are not at all matching, then the value will be 0. So there will be no similarity. For those whom it is not clear, just focus on this bottom image. It will be clear for you. Now this is actually the real example of a fingerprint. This is a fingerprint of compound number A, fingerprint of compound number B. Now as per our definition, now for suppose if I consider this as the criteria of benzene ring or hydroxyl group. So in compound number 1, benzene ring is present, here it is not present. Hydroxyl group not present in both of them. Similarly, other compounds. So how much is A? A is equal to 8. Means B is set to 1 in molecule 8. 1, 2, 3, 5, 6, 7, 8. A is equal to 8. B is equal to similarly 6. How much is C? C is where both the things are matching. So 1, 1. Here it is matching. So 2, 3, 4 and 5. So C is becoming 5. Okay. So based on this, you could calculate SAB 5 divided by 8 plus 6 minus 5 means I am getting the Tanimoto coefficient value of 0.56. So based on this, you can say the compound number A is matching with compound number B to a level of 56%. Okay. Just try this example. Similarity search for compound number 1 and 2. Create this table for these different 8 fragments and tell me what will be the value of SAB. SAB is C divided by A plus B minus C. Tell me in 1 minute. Okay. So many of you have said it's 60%. So those I hope many of you would have got the correct answer. Only some of it might be confusing to you. Always like here, if you are looking for benzene ring, it is matching in both the things. For this carboxylic acid group, like here you can see. This is a little bit confusing. Like you can see here, there is no. I cannot delete it. So here you have to look for all the times single bonds are given. So even though some of you might have tried to match with here, just you can consider there is a double bond. So this could not be matched. So in both the things, it is not present. There are things like this. It's present only in this particular compound and not in this one. So accordingly, you are getting A is equal to 5, B is equal to 3, and C is equal to this 1, 2, and 3. So SAB is coming 0.6. Okay, so I guess I hope you got the idea how the two things are actually matched and scored. Now this is also what we have learned about the similarity search. This is just based on the 2D fingerprint. So this should be called as 2D similarity search. There are again ways of 3D similarity search. So again, like in the earlier example of 3D pharmacophore, I mentioned to you that along with the their specific geometry. So like here you have tried to match the fragments. So fragments will be matched in the 3D similarity search, but along with that, these spatial features will be also matched, like hydrogen bond donors and all those groups. So there will be Tanimoto coefficient for your fragments and Tanimoto coefficient for your features, and both the thing will be combined together. So that is called as something called as combo Tanimoto, and the value will be out of 2.0, out of 2. Here actually you have value out of 1, like 0.56. There the values will be out of 2. So even these kind of things can be estimated, like later on when we'll be talking about some mini project. So even some of you could actually try to explain how to do this 3D similarity search. This also like one or two group could choose as your topic. and try to go into the details of this. So for today, this much. If you have any question, you can ask.